So now let us discuss about the two types of processors. We'll discuss one fixed point processor, a DSP processor from a Texas Instrument, that is TMS 320C54XX family. Then we'll discuss one floating point processor. Okay, then we'll discuss one floating point processor. Okay, not will not go into specific. Okay, so probably as a student you will be more interested in the CPU and the way the memory has been separated rather than all the pins and okay. Anyway, let us get started. So what do you see? What's different compared to any other processor? What do you feel is different in this particular processor? So the staggering difference you can see here is the various amount of buses. Now let us understand this from a situation of normal filtering. Say I want to do this particular convolution y of n equal to x of k, h of k, x of n minus k. Okay, let us say I have to do this h of k, x of n minus k sort of thing. And x of n minus k, that means the input data which keeps streaming. Okay, so you have to uh, what you have to do is go on multiply and add. Okay, now let us try to understand the processor, why the architecture is so designed keeping in mind this particular operation. So most of the times whenever you do operations in a DSP processor, it is either convolution or it is okay. So for this particular operation, so how do you want your data to be? So at that time it would have been good if at all. Now say the opcode for this particular instruction will be residing in some memory location, right? It will be residing in some memory location. So an attempt has been made to load that instruction and execute the entire instruction in a single cycle. Okay, by having a separate program memory bus. So what is program memory bus? From this program memory bus, the opcode for that entire instruction will be loaded, and then the two operands. So what operands do we need here? So h of k is one operand, x of k is another operand. So both of these operands will be loaded from C and D. Okay, from C and D, that is the data memory. And then the result, that is y of n, will be written through this particular another bus. So got this particular thing. So to be able to implement this entire instruction in a single cycle, we need four buses. One bus, the program bus for fetching the instruction opcode, two buses for fetch the operands, and another bus to store the resulting data. Okay, so that explains the data bus. By the way, there is a address bus, right? Because x of k, h of k, even y of k or the opcode. So you have to give the address, then you have to read the data. So you might have seen in 8051 there was this one bus, right, which where half of it was multiplexed into address and the remaining for the data. So that was annoying, would take double the time. So this one much faster, of course a costlier, not so efficient implementation, but the stress is on the speed. Okay, so that explains the buses. Not only the buses, you have to have the memory also, right, separated. So you can see here there is separate memory to store the opcodes and separate memory to load the store the operands. You can see here two operands C and D are connecting to this particular processor. You can see the operands C and D, two operands x of k or h of k, they go to this particular bus here, they go to this particular bus here, and finally the process data that goes again into the data memory. Okay, so that allows, and moreover nowadays you get this memory is called as dual access memory. Say you happen to have a RAM, what is the usual method? You give the address on the address buffer, read the data on the data buffer. So in a cycle technically you can read only one data, but nowadays you get this particular dual access RAMs where the operation, the hardware is so optimized that symbolically you can read two operands at a time, or you can read or write operands at a time, called as dual access. Nowadays you might have seen what's that DDR RAM, right? Double data rate, something like that. Okay, so something like that. And anything else, by the way, anything staggering other than that? So the first point we made was whole lot of program and data buses. This was the first point that was important and different. Second point was this particular thing, having a separate program memory and data memory rather than a one human architecture where everything was, a jugadu sort of thing. Okay. Then other thing that we can see here is uh, ALU. There is a conventional ALU. Other than that, there is something called as a data address generator and something called as a program address generator. What is this address generator? You might have seen this particular thing, right? Say you wanted to loop through some set of instructions 20 times. Then what do? You will initialize some pointers, increment source pointer by 1, increment destination pointer by 1, decrement the counter by 1. Okay, that's what you would do, right? Who would do this particular incrementing? Usually the load would have been on the normal ALU. Okay, normal ALU. So that while you are doing this petty, so while you do this petty incrementing thing, you are the all other processes have to wait. So here not like that. So if at all you have your multiplication or addition sort of, a larger task at hand, they need not be held ransom by the petty source or destination pointer increments or decrement. That's why a program address generators, is it that much easy? Now suppose you have to run through this particular instruction. Say there are some 5 instructions and say there is a jump. Okay, jump to a previous label. So when you have to do this, you have to keep track of, where exactly to jump, or if there is a subroutine call, right? You remember the procedures where you have to go for a different set of program somewhere in the memory. So generating program address to a new location, so it becomes very important. And in all these cases, usually otherwise in a general purpose processor, your normal ALU would be used. Here a separate program address generators are there. Same is the case with data also. If at all you're using pointers and then you're incrementing pointers, where actually is your data? To do that also, okay, to control the direction of the program, use the program address generator, uh, other than exclusive one, other than your conventional ALU. And then for generating the actual data pointers, you use data address generator. So this was the third very, very staggering thing that we noticed. The fourth thing that we want to notice here is multiple ALUs. You can see here, this address data generator is also an ALU, which can either increment by 1, decrement by 1, increment by certain number indicated by a label, jump to a subroutine. So again, changing the location of the program counter. That's also an ALU. Then you have your normal ALU, which can do all sorts of. Then you have a MAC unit. This MAC unit also contains a multiplier, then an accumulator. Okay, this accumulator also different from your ALU. Then there is a shift unit. Okay, what's the deal with the shift unit? Why would you do a shift unit? Why are we making such a big deal about shift unit? As we discussed earlier in the previous lecture, if at all you are trying to do floating point multiplication, floating point additions, what do you have to do? You may have to sometimes, adjust the exponents. You may have to adjust the mantises, sorry, to adjust the decimal dot. And you want to multiply by 2, multiply by 4, divide by 2, divide by 4, divide by 16. How are you going to do it? You are not going to do it the normal way. You will be using shifts usually. You will realize the normal multiplication or divisions whenever you are doing, you will not usually multiply by a 5 or divide by 7. You rather multiply by 8 or a 4 or divide by 8 or a 16 or a 4, so that those multiplications can be carried out by simple shift operations. Okay, that's where a shift comes into picture. The first example that we saw in the floating point operations, right? You multiplied two 3-bit numbers, you got your answer as 6, but then you wanted the initial, last 2 bits to be removed, and the sign extended 1 bit, you wanted it to be removed. So how are you going to do those particular things? You are going to do it using shift operations only. So shift unit is also an ALU. So this is another fourth very, very staggering fact that you will observe. So this particular TMS processor, okay, a very interesting one. So multiple buses was the first thing, and other than this address generators, program address generators and data address generator, that was second thing. Memory is separated into program memory and data memory, that was third interesting thing. Multiple ALUs, a dedicated multiplier and shifter, that was another interesting thing. Let us see what else is interesting into, and let us go into something very specific. Okay, so anything 16-bit data, okay, 16-bit data. on-chip program and data memory. That's cool. On-chip program memory and data memory. Other than your general purpose registers, we know you have them on-chip. They are going to be very fast. Okay. On-chip memories are always faster. So that's cool. Other than that, anything specific? C and D data memory buses. Yeah, multiple buses he is talking about. 40-bit accumulators is something very interesting. 40-bit accumulators is why it is 40. You see, the processor is 16-bit, right? Processor is 16-bit. Why do you need a 40-bit accumulator? Because as I was telling, if at all you're adding 10 two-digit numbers, if at all you're adding 10 two-digit numbers, right? 91, 93, 86, 43, 49, that number can go to 999. So adding one digit extra will allow you to add 10 numbers. Adding two digits extra will allow you to add 100 numbers. So DSP is all about MAC operations. So having additional bits more than 16 will let you loop through larger sets. If at all you want to perform a 1024 point DFT, you can imagine, okay, if at all your data is 16-bit data and you may have to do 1023 number of additions, your answer may easily increase by another 10 bits, right? So that is why a larger accumulator size, it defends. Then afterwards, what can do? Yes, it can be broken into pieces of 16, 1, 2, 3 pieces, and it can be stored, by the way. That's easy. And second thing is a 17 cross 17 multiplier. Your data is 16-bit. Why are you bothered about, why would you like to go for a 17-bit multiplier? Here also this is interesting. So you don't have to lose on the precision. That's what he's talking about. You don't have to lose on the precision. Then a barrel shifter, that to 40-bit. So we were discussing earlier, suppose you want to multiply two 16-bit numbers. Okay, what's going to happen? The answer is going to be 32. Answer is going to be a 32-bit. But then afterwards you want to adjust it, accumulate, what is it, exponents, maybe the mantis. Then you may have to shift them to the left side or the right side. So then you may have to use this particular 40-bit shifters, or you got a data of 40-bit in the accumulator. First 16 bits you want to read onto some register. How are you going to do it? Maybe shifter will be helpful. So shifter, okay, the sizes is very interesting. That's it. A very interesting processor, the TMS 320C 54XX. So I have told you the very important points. Okay. Now let us see what about a floating point processor. So a fixed point processor here, maybe this one sticks to a Q15 notation. Okay. So this will be sticking to a Q15 notation. Whereas we saw what was the issue with the Q15 notation. So the processor is very simple, maybe economical compared to a floating point processor, but the entire burden is on the programmer. Whereas if at all it is a floating point processor, then the programmer can be relieved. The processor is going to be sort of complicated. Let us see. The advantages of using the floating point processor includes, what do they say? Getting rid of finite word length effects such as overflows, round of errors, truncation errors, because you have a very large dynamic range that adds to the advantage. Coefficient quantization error won't happen, right? As I told you in a Q15 notation, 2 to the power minus 15. That's the kind of error you can have. So that's a catch here. It is not there. So in terms of coding, no need to scale the input samples to avoid overflow. Okay, so the programming is going to be much more simple. Okay, programming is going to be much more simple. Okay, so let us see a processor. So let us see the processor here. Okay, so in this particular processor, anything interesting do you find? Uh, well, the only thing is floating point operation. So there is a integer floating point multiplier, integer a floating point ALU. That means ALU is capable of doing both the operation. That's what we needed, right? Rest all the places, maybe the data is going to be very similar. Okay. Then afterwards, extended precision registers. 8 extended precision registers are going to be there. That means extended precision is usually in TMS 320C 64XX. Extended precision maintained 54x 80 bits. Okay, so there is 32-bit register, there is 64, then there is 80. Okay, so in IEEE format also you saw there is single precision 32, double precision 64. Then there is something called as extended precision. Depends, the number depends from processor to processor. Then there were address generators, yeah, then auxiliary registers and control registers. Let us see what specifically are the features here. Then remaining things are same as the previous processor, having a separate a DMA block, then program, then separate RAMs are interesting, separate RAMs are interesting. Okay, then a ROM. Usually ROM is supposed to hold those constants. What sort of constants? So you design a 13th order filter or a 65 order filter. Coefficients do not change during the program, right? So they are supposed to be there in ROM. Whereas your data, input data xfn and whatever I stream on the output yfn, they keep changing. They usually go into ram. And then if at all you want to find a dft, then the cos 3 pi by 64, cos 7 pi by 64, right? Those coefficients, they usually go into rom. Okay, they usually go in, they do not change, right? They usually go into rom as a lookup table, whereas the remaining data xfn and the output yfn, they usually go into RAM. Okay, that's the thing. And the DMA. So this is a feature. This has got nothing to do with DSP, I guess. Okay, this has got nothing to do with DSP. Okay, so that was about the processor. Anyway, let us see if at all there is anything interesting. So anything else. So other than being a floating point processor, this is interesting here. Dual access on chip memory. Okay, dual access means, as I told you, you do not have to give a single address to read a single data. You can at a time give two addresses and read two data simultaneously. That's going to make it faster. Okay, that's going to make the thing process operation faster. Other than that, any other advantage here? Separate buses for program and memory. DMA, fine, we will write that. DMA is fine, we'll write that. Then floating point capacity, operation in number of very large dynamic range. Yeah, dynamic range, yes. Then implementation of DSP algorithms without worrying about the problems such as overflow and coefficient quantization. Okay, we will write that. Then three floating point formats are supported. Same short 16-bit floating point format with 4 exponent, 1 sign and 11 Mantissa, 32-bit single precision. See, there is single precision, there is short, and then there is extended precision. So when the in the block diagram, when it said extended precision, it's not 80 for this particular processor, it is 40-bit. For this particular processor, 32-bit is single precision, 40-bit is extended precision with 8 exponent bits and 31 fraction bit, 1 sign bits. Okay, and let me tell you, let me clarify again. They are not the IEEE 754 standards. We are not bothered here. Okay, the beauty of this particular module is you just have to remember the block diagram and the points. You do not have to bother about the op codes or the operands, nothing like that. Okay, so that was about the TMS processor. Anything else that I am missing? Yes. So in the next lecture, which I am going to upload, I will be talking about what is the deal if at all you want to implement an FIR or a IIR system in a filter that is going to use a fixed point representation. Okay, what sort of issues will come? Usually, what's the catch with a fixed point processor? You stick to Q notation, and the number cannot exceed 1, otherwise there will be overflow. You should have to scale the inputs and you have to later scale the outputs once you get the entire process done. That we'll do in the next lecture. Till then, bye.